we go. So this is the 7th lecture, and after discussing all these simple, let's say, simple architectures, such as just the multilayer perceptron, then we talk about the recurrent neural networks quite extensively, 1.5 lectures roughly, and everything seems to be like obsolete now in a way, because in a couple of years ago, well, actually already like 7 years ago, 7, 8 almost. Well, Jesus, 7. Time flies. The so-called transformer architecture showed up in some setups, and it turned out to be very powerful. And actually, this is the architecture which is powering all these AI these days, all these large language models and other like vision models and so on. There's different architectures as well for generating images, for example, the diffusion architectures. But in language processing, this is the architecture everybody's using these days. So I think we should spend a considerable amount of time to understand this thing and to dig deeper and to know all these nitty-gritty details of this architecture. At the end of the day, it's just a neural network, and at the end of the day, it's just a combinational graph with parameters which we are learning by training on some training data. Good, but let me just start with a little bit of motivation. So what makes these? So what are like key kind of aspects from other fields that have been transported here to make these architectures, the transformers, actually powerful? So we saw examples of that. So one example is multitask learning. Not example. One let's say paradigm is multitask learning, and it's actually an old concept. Like here's a paper from 1990s. And we saw it already in BERT embeddings. So multitask learning means I might have multiple tasks for my network to perform, like sentiment analysis, like text summarization, I don't know, like name all these tasks. And maybe I don't want to train a special network for each of these tasks, like having a separate architecture for a sentiment and so on. Maybe I want to have something shared, like shared understanding for a language in general, and then for each of these tasks having something specialized. So maybe some specialized things for task 1, task 2, or maybe the network can solve actually all tasks at once. That would be excellent. And the idea here is very simple. Like you can basically take a network. So here's sort of like a a neural network. There's some input, maybe text. Here's some outputs task, like prediction 1, prediction 2. And the idea is that we can learn these tasks in parallel and use some shared representation. So the idea is that the network is sort of like a deep neural network. So there are some like deep layers here and some, let's say, close to the task layers here. And we would say, well, you know what, like everything which is like down here should be shared for all these tasks. And maybe there's some parts of the architecture for one task and some other tasks and some parts of the architecture for other tasks and so on. So, and we would basically train the network on all these tasks. Maybe we can start with first one, then the second one, or flipping around and so on. And while doing so, we would learn very good representations which are generic. So they wouldn't, these representations, maybe like word embeddings here, they could be used for multiple tasks as one. So it would generalize much better than we would expect. Okay, does it make sense intuitively? And one example in early examples in natural language processing of multitask learning is that one. So we have here a neural network, which is, so there's some input again, data for some main task. There are a couple of layers we're coming up. And the main task is some syntactic chunking or tagging. So some sort of like part of speech, no, not part of speech, some sort of highlighting chunks of text into like a chunk of text, like could be a multi-word expressions, for example, whatever, some sort of task which is sort of like high level, and this is the main task we wanna perform with the network. But we also might have data for some additional tasks, such as part of speech tagging, right? I mean, part of speech tagging, noun, verb, and things like that. So it's sort of like low-level task where you assign something to each word, and you want to learn this task. It's more like, I would say not linguistic, but more like low level, like bound to the words. And under Sogard and Jav Goldberg in their ACL paper 2016, like, almost 10 years ago, showed that actually, if you start training your network, your let's say lower layers on this lower task, lower in terms like simpler task, then you will learn a good representation for task which is somehow which could base on the other task. Like syntactic chunking has something to do with parse-to-speech tagging. It's not the same, But while training on part of speech tagging, we learn something in the network that will be helpful for the other task. So if there is a hierarchy between different tasks, then if we train on one task, we can benefit in the other. It may intuitively make sense, and these were one of the early examples of doing so for learning good representation, because the idea is that we train a network which will generalize well for actually many things. Okay, does it make sense intuitively? Good. It wasn't always like that. I mean, I remember these, back in these days, it wasn't clear whether it's called like transfer learning or multitask learning, whether it's really helpful or not. And in some tasks it wasn't, in some tasks it were, but it turned out it's actually a very nice paradigm. So, which tells me I'm getting older a little bit now. I mean, because I remember these days. Anyway, so we can also use it for maybe some much higher, well, not higher, much more complicated tasks. So for example, we can take a corpus for natural language inference. So you remember what natural language inference is? This is like this hypothesis and, text and hypothesis, and where there's an entailment, like if you read the text, you would say the hypothesis is true, or contradiction, or irrelevant. So there's this SNLI data set, which you should be or could be familiar with. And you can train, or here they use some LSTM. So this is like recurrent neural network, and they train the LSTM to perform this NLI task. So the network, given the input, two sentences would say it's contradiction, entailment, or not. And they then took this network and use it for other tasks, train it on paraphrase detection, which means given two sentences, can you tell whether sentence B is just a paraphrase of sentence A? So basically, like, do they have the same meaning or so? Or there's another task, caption image retrieval. So given an image, can you retrieve? Can you tell which caption fits the image from a? Oops, what happened? It's very fragile. Which okay, I'm gonna touch it. Which image should fit the picture? And by having this pre-trained, these final tasks perform much better than they just there wouldn't be any transfer from other tasks. So the pre-training actually helps in many tasks, and it's called I would call it like transfer learning, which is you learn on something and transfer to some other task and just continue training on that. Okay, so this seems like obvious to do, but if you can, this is a paradigm which is actually essential for any deep learning these days. If you think about this, it's similar as word embeddings, where word embeddings, we train word embeddings just by what? Just word2vec, for example. We train static word embeddings, and then we use these word embeddings in some other task as a representation of the input. So it's also like transfer learning, yes.
So what is going into the other network? So just the output of the...
Oh, no. It's basically the same pre-trained network. So you pre-train the network, forget about these tasks and data, and you plug it here. You take the same network and start training on the other data set, like paraphrase corpus, and try to detect paraphrases. You basically take the weights, sort of, or the same kind of pre-trained model from the first task, and just start using it for the other task. The same architecture, and the weights are not random anymore. They were random when you started training on the first task, but now they are pre-trained from the first task, and you can start sort of fine-tuning them on the second task. Does that make sense? Okay, cool. Okay, so this is interesting. So this is the first paradigm. The second paradigm, which is interesting or important for transformers, is the actual bottlenecks of recurrent neural networks. So, we spend some time on RNN and saying like, oh, RNNs are actually quite nice because they can take like all the different lengths of the input sentences and just have the same weight, same architecture, and things like that. That's true, and it will get you somewhere. It will get you far, but it's also very slow. And the reason for RNNs being slow is that they are sequential in nature. So you have to do like a first token, then the next token, then the next, and so on. So all the computations have to be sequential, token by token by token by token. So although you can do, I mean, all these computations in each cell or each step, all the multiplications of matrices can be parallelized. The overall thing cannot be parallelized. So this is a bottleneck basically on the computational bottleneck, which means you have to wait longer. You cannot parallelize stuff on GPUs easily for RNNs. So maybe we just might have just better and faster architectures, which will be the transformers. So this is RNNs are actually, I mean, they might be powerful, but they just don't scale that well as some other architectures, such as the transformers we will see later. So they are now, I would say, like completely out of fashion for text processing. But I believe they are like conceptually interesting to know about them. So that's why we covered them in the lectures. So and also the last point, I mean, it's kind of disconnected from that, are these disadvantages of static word embedding. So what are the disadvantages of static word embeddings? Static word embeddings are great. Berlin versus, Berlin to Germany is like Paris to France, all these things. But what is the disadvantages of static word embeddings? Yeah. If a word has multiple meaning, you're kind of stuck just with one vector, which also means it's a symptom of something much more problematic, which is they are context independent. That's a problem. You cannot take a context of a word and learn some different word embedding in the context. Not learn, but each word will have the same word embedding, static word embedding, regardless of the context, which means, of course, you feel like the bank, I was sitting on the bank should have different, hopefully maybe different embeddings in this context than in some other context, like I went to the bank. When static word embeddings, they have the same word, the same embedding vector. So this is the disadvantage. Okay, so we need to solve this. And we're going to talk about the BERT architecture, which stands for bidirectional encoder representations for transformers. I don't know if this is, I don't know if they first came up with this abbreviation or the title, but everybody just went crazy. And if you know the, how's it called, the Sesame Street, like the bird from the Sesame Street, this puppet. So all the papers back in then were just have like puppet names, like BERT and I don't know, Roberta and all these kind of, and everybody was putting pictures of these, Sesame Street characters. Anyways, so this is the BERT architecture, and just to see like why is it important? Why was it a game changer in anything? So it's just a different architecture, but it got like the best state-of-the-art results on 11 language tasks at once, including some language understanding by 7% up, natural language inference by almost 5% up, question answering by 1.5 or 5% absolute improvement. Just the change of architecture and like clever pre-training of the architecture will push your numbers from 70% to 75, from 85 from, and stuff like that, which is a game changer because you don't have to have like more annotated data or I don't know, like it's just a clever architecture and pre-training. That made the difference. So, and after this lecture, we should be able to build BERT actually. Like we're gonna talk about the architecture and how this thing works under the hood. Okay, and this is the motivation why it's important. It will give you like much better results than pre-training RNNs, for example, LSTMs or multi-layer perceptrons. Okay, so let's have a look into the encoder architecture in detail. So why is it called encoder? What do you think is, why is it called encoder? What could encoder do? Yeah. Encode the input. Yes, that's it. Like it takes the input and encode it into what? Maybe a vector. Maybe something else. Maybe something some representation which is helpful for for doing some downstream tasks. Okay, and that's actually very very true. So BERT is training contextualized word embeddings. So if we have an input token like, I don't know, lorem ipsum or the cat set on the mat, we have a couple of tokens, 1, 2, 3, 4, and so on. Then there is this black box called BERT, whatever it is. I mean, we'll look deeper, but what's coming out of that? Sometimes there's coming something else, but most of the time what you're getting is that for each word you have contextual representation of token 1. So some sort of word embedding, but this word embedding takes all the tokens into account. So it's like this is what we want for this is solving the disadvantage of static word embeddings, because for static word embeddings you would have for token 1, oh yeah, I just look it up from the embedding matrix and it's going to be a vector. But here, you know, it will take into account all the context around. So it will learn, it will give you, not learn, it will give you contextualized word embeddings, which will be very much helpful for anything what you're gonna do with them down the road. For example, I don't know, like classification, prediction of sentiment and stuff like that. So contextualized word embeddings or token embeddings, because what's coming in is not really words, these are tokens or subword units, which we talked about already. And it can be applied to many downstream tasks. We'll get to that. So let's dig deeper and find out, you know, how this actually works. Like, okay, we have a couple of tokens. We need the same number of outputs. What do you? But let's talk about one disadvantage already. So what do you see? The k seems to be some defined number. So the length. The problem here is that we kind of forget all these advantages of RNN, like different lengths of the input, and for this BERT model, the input always has the same length. So all the input data, all the documents will have a maximal length of some sort of k, something like that. So if you have shorter sentences, you're good. What you're gonna do with shorter sentences? Let's say you have a k of, let's say the input length is, I don't know, like 512, and you have the sentence, the cat said. How do you want to make it fit into 512 tokens? Like the simplest solution. Yeah.
Have just the rest be like some sort of null token.
So the rest will be like you extend it to be 512, and you're proposing?
For the rest of the unused tokens, just use like some sort of null token.
Null token? Yeah, exactly. We call it padding. And you would use some sort of something like which corresponds to zeros or something, some empty token, so nothing. So you just extend it. How about like if it's longer than 512? Yeah. You have troubles. If it's longer, you're in troubles, and then you can make like a hacky solution or just ignore this completely. So the hacky solution is somehow like, oh, I split it, use two models, or do some hierarchical models and all these crazy things. Or you just say, you know what? If it's over 212, I just cut it. And you ignore the rest of the document. And sometimes it's okay. Sometimes maybe you just need a first. If you do like sentiment analysis on movie reviews, they are much shorter than 212 tokens, and then that's okay because you can guess the outcome in the from the beginning already. Sometimes, if you have long text, for example, in the legal domain where you have core decisions which are super long, you have to have some different architectures maybe or some hacks around. So this is the disadvantage, like right away. The limitation is like you have limited input context. You have to live with that. But there's so many advantages. So let's look deeper into the BERT architecture. So how it looks on the first zoom in is that we have a excuse me, we have a bunch of tokens. I'm using n here as the input size. Why not? So we have a bunch of input tokens, and we're gonna change them into some input embeddings, something like static word embeddings or static token embeddings. There will be much more. And then we get some sort of matrix. So for each word, like the cat said, we get a vector, 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 which is going to be our x. So this is it. And then we're going to stack it through something which we call transformer encoder layer. And there's L of them. So we're repeating them. And basically each layer will learn something, will produce something a little bit different. But at the end of the day, what we get is a matrix of the same size as, or excuse me, same number of rows basically as the input. So for each token, we get one row in the matrix, which will correspond to its contextualized BERT embedding. Okay, questions? Yes. Exactly. We'll talk about the input embeddings in a few seconds. What exactly this will be? It will be something static. I mean, something it will be something bound to each token individually, ignoring the context, because there's no way to mix them together easily. But in the transformer layers, they will be mixed together.
Transform it into something that has context and put the words in
Exactly.
Actual context.
Exactly. The transformer will take the context, will model the context somehow. We're sort of learning better representation of each token in context of the other tokens. I think this is the cleanest way to describe it. But I think your intuition is correct. Yes. Okay, good. So let's have a look into the details. Some notation. Oh, okay, some notation details. So we'll simplify the notations. So just set of n numbers, it's gonna be just this in these brackets. So for example, t in n means like t for 1 to n. So just to make this math shorter. Okay. So if you struggle then with understanding some formulas, you can go back and look at these abbreviations here. Okay, so let's build. I mean, at the end of the day, this whole thing is a function from xn to this. So it's a function. So let's build it as a function. Let's build this as it's an algorithm. So let's build this as an algorithm because this is what it is. So what's coming in? So we're starting with a function e transformer, encoder transformer. What's coming in is are the input tokens, and what's coming out is some matrix. Oh, maybe some parameters. Yeah, all trainable parameters. So this is very fancy W. There will be very many parameters because depending on number of layers and all these things, it's going to be a lot of parameters. And what's coming out is typically an embedding vector for each input token. This is what we discussed in the previous slide. Or we might actually use it for not generating words. We can use it for projecting these word embeddings into words, basically. So we're going to project it into the size of the vocabulary. We will see later exactly why we're doing this. But typically, when we use BERT, which is already trained, we get these contextualized BERT embeddings. So this is the function we're going to use. So let's have a look now. So let me zoom out again. Let's start with this input embedding, which we're asking, like, what is this exactly? So we'll have a look deeper into these input embeddings now. So we have the very famous sentence again, the cat said. And what are those numbers? What do you think? Yeah. Exactly. This is the index of each word in the vocabulary. So we have to assume we have some vocabulary, which is size, I don't know, 50,000, something like that. So these are the indices of those words, and we change them into some input embeddings. So this will be for each word. This will be embedding for token 1, token 2, and token 3. So the question is what exactly these embeddings are going to be. And we're going to use multiple or two different variants of these input embeddings. So one input embeddings will be the standard, let's say, static word embeddings, like could be static embeddings. I mean, basically, this is a trainable parameter. So there will be some matrix, let's say E, with all these embeddings, and we're gonna train this by backpropagation. So we start randomly, and then this is the same as we had in the language modeling. So look up in this embedding matrix to get an embedding for each particular token. So this is the first part, like input embedding or token embedding. But we need something else here, and the motivation for that is maybe will be clearer later. But we're also going to add a thing called positional embeddings, which is at the end very simple, but at the first time it makes no sense. But then we will understand why it makes sense. So apart from these token embeddings, like what is the representation of the bank or things like that, we have also for each input position t. So t is like really for position 1, 2, 3, 4, up until the length, the L. We train an embedding vector, which is just a bunch of numbers. So we have for each position, and here really we mean like number 1. So we have a number 1 position, and number 1 is gonna have some embedding, like this one. It's gonna have some embedding. And this is important because we want to show the model which part of the input is it going to deal with. So if we don't add these positional embeddings, by the choice of later the architecture of these transformer layers, the model wouldn't be able to distinguish the, it would be time invariant. So it wouldn't be able to take into account what comes after what. We will see later some multiplication of matrices, which this will become clear why this is so, but we need to add these positional embeddings to actually show which words come after which words. And this is not important. I mean, it was originally proposed for something else and showed like it's super, super fast, but now, whatever, it doesn't matter. Does CNN, does it ring a bell for anybody? Convolutional neural networks? Computer vision? Yeah, okay. So, yes?
I have a question.
Yes.
So, could we say that maybe we didn't need this positional embedding in RNNs because in RNNs they weren't parallel? They sort of implicitly had this order?
Exactly. In RNN, you didn't need any sort of positional embeddings because you knew exactly the timestamp at which you were. So you know which word comes after the previous context because this is how you model basically the network. But here we're cramping everything into, I mean, we look up the word embeddings, and yeah, I mean, somehow it should be clear what comes after what. E2 should come after E1 and E3 after E1 and E2. But later on, we will be doing some, all these attention and things like that. And then it will turn out that all these operations are time invariant, which means if we shuffle these words, we would get basically sort of the same result in a way. So we need to add these positional embeddings to take this into account. How are we going to add them together is basically we sum them up. So L is the length of the document. And for each token, we take this is horrible notation, but this is just lookup of these of the token embeddings. Like this is this. We look up the token embedding for each word. So for example, for word number 1, we get this embedding. And then we add simply a vector of the positional embedding. So we say, oh, for token at position 1, the embedding for position 1 is something like that, and we add these two vectors together. So this is how we make sure that what's coming out of this, each embedding for each token, is both the content of the word, which is coming from the static word embeddings, and its position together. Okay, so this is how we make sure that if we have, for example, cat at position 1 and cat, at position 22, these would already, in the input layer, have different embeddings because, I mean, the cat will have the same token embedding, but the position embedding will be different for 1 and 22, which already tells us these two words are different because they are in different position in the input sentence. So this makes already sure that this, there will be some context taken into account at least. So we're starting with the position. Does it make sense? Any questions? Yes.
I have a slight question.
Yeah.
Didn't we say earlier when we were talking about RNNs that this time invariance was actually something useful?
Yeah. That's right. I mean, we're talking about RNN saying like time invariance is useful, but it was like whether a sequence of tokens happen at the beginning of the document or at the end of the document, maybe there's some local dependencies are important. So it doesn't matter whether it's at the beginning or at the end. But here, what do you mean by the time invariance is that all these operations later on all these operations here in the transformer encoder layer, here, all the operations would work the same regardless of whether the tokens are, shuffled in a random way. So here in the encoder layers, it doesn't distinguish between words at position 1 or 3, which will then it actually would like a bag of tokens in a way. So we need to make sure that what's coming in are some embeddings which already encode the position already. Kind of to we in RNNs we had this transition from step to step, but now we don't have it. So we need to make sure that we somehow distinguish these words. Okay, cool. Good. So this is the first block. So for each word we get some input word embedding and we stack them row-wise. What does it mean? Just like we did before here. So we stack them row-wise. So for each word, it's row and it's sort of in matrix representation. So number of rows is the number of input tokens, and the number of columns is the sort of the dimensionality of these embeddings, which we can design. Could be, I don't know, 300,000, whatever, some parameter. Okay. So far, so good. So we have the input. So this is the first thing. So we finished the input embeddings. Yes.
Have any meaning in this model? So like in the embedding we discussed in the last week. So
I guess so. I guess it will learn some context-independent sort of representation of these input tokens.
So it's like similar words have similar directions.
It will be. I believe it will be similar by static word embeddings. It will be, if you train this, there should be something which is similar to static word embeddings. Actually, I don't recall now like papers exploring this, but there must be some. I mean, somebody absolutely look into that and like look into go. And maybe I'm not 100% sure, but I believe you can actually initialize these static word embeddings by using word2vec. So you don't have to start learning this from scratch in the transformer by random embedding matrix. I think you can already take some word2vec pre-trained embeddings and just plug it in there as the initial weights. I'm not 100% sure now. I would need to double check, but I'm almost sure that somebody tried it. It would make sense, of course. Yeah. Okay, cool. So let's have a look into transformer encoder layer, which is repeated L times, where L is a parameter. I think in the BERT model was 12 or 24. Yeah, it looks like a very low number, but the trick is like there's very many parameters in there. So GPU is your bottleneck here. How many? I mean, the more layers, the better, but it needs to fit some GPUs. So let's have a look into this transformer encoder layer. So let's just extend our algorithm. So so far we have the input turned into input embeddings and stacked together, and then we're gonna repeat something L times. So let's look. Okay, wow, looks horrible at the first sight, but okay, let's dig deeper. So again, this is just sanity check. What is this X again? What is this X? Yeah. 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 So it's basically a matrix. Number of rows is number of tokens. So each row corresponds always to a token, and the columns is some sort of dimensionality of these embeddings. Yes, exactly. What's coming out is the same dimensionality. Again, the same number of tokens and the same dimensionality of some embeddings. So this is the idea. I mean, basically, what's the size of coming in is the size of coming out, and always each row corresponds to input token, always, because what you want to learn is like contextualized token embedding. So there have to be this correspondence. Okay, so this is good. So this is some sort of bunch of vectors of same size. Okay, so it's taking two directions here, to this thing called multi-head self-attention, and it's going to the sum. So this is interesting. Now we see that it's actually, still like a DAG. It's direct acyclic graph, and it goes to two parallel rows. Here, we're just using the input and keep it as it is, and sum it together with output of some like subunit here. So the X is going to something multi-head self-attention. We'll look deeper what it is. And here what's coming out is the same bunch of vectors. So size of the length of the input times some dimensionality of that. And we just sum them up. And then it goes through some normalization. Okay, we'll have to look into that. Then there's another branching. So again, we keep the same input. Now it goes through something else. We sum them up and there's something else. So basically we have like, there is some sort of like highway here where the input is going through the network. So there is like a direct path. And we're at a couple of points here. We're just taking this input and do some computations on that and add it back. And here we add some computations and add it back. So the information flows through the network on some sort of highway. And also it goes, detours to learn something else. And we'll come to that later how it's called. But basically there's, this is the flow of information. So does it make sense now a little bit? I mean, without knowing what these things are, this is just a flow of the information through this encoder layer. Okay, questions? Sounds good. So let's focus on this multi-head self-attention. So, okay, but we have so let's put it into algorithm. So the first thing was that we use the original X and add this output. So this is this function. We take the X and add the output of the X, and it's called residual connection. So residual connection means like we're taking the original and summing with some other output. Okay, so let's have a look into this multi-head self-attention. So again, the input is a bunch of, what is this again? The same, like bunch of token embeddings, number of words, times size of the columns. And what we're doing here is that we're splitting this again into several branches, and they actually are the same sort of architecture. All of them have different parameters, obviously, but we call them the attention head. There's head 1, 2, and H. And again, H is something like, I don't know, could be 12, I don't know, 64, depending on how many, how much compute you have. And after that, we're gonna stack them together and project into something else. Okay, so basically the output of these will be some matrices, and we're gonna stack them together to produce some other matrix and then project into something else. Why not? I mean, this is just some linear algebra. What's important here? We have all these attention head, attention head, attention head, attention head. So they're running in parallel. And they, as you might guess, I mean, this is the same algorithm. So the attention head will be the same sort of transformation of the input. So what happens if you have an X and run it through parallel, several parallel heads, which is the same function? What you will get at the end should be the same output, unless each of those has different parameters, right? So basically it means you have this several neural networks with the same architecture, but they are initialized differently, so they will learn different parameters, so they will learn some other functions of the input. So, and you're hoping that if you learn 20 different functions, each of them will give you something different, because each of them is initialized differently at random, so they will end up with different parameters. And they will learn some different functions which will be helpful for learning this representation of this input. If you have, that's basically, it means like, each time you shoot into the dark by random initialization, and you hope that each time you will get a different function which will give you something interesting. Yeah.
Question. Why here, like y1 is a vector?
Why? I think this is a matrix. This is some sort of matrix.
Oh, okay. And y is also.
Yeah. These are matrices.
And then they're stacked all together.
And they're stacked together. I think we'll get to that. So we're gonna concatenate them. Excuse me. We're gonna concatenate them along the rows. So basically, stacking them along the rows means we're gonna take this is one matrix, this is another matrix, and we just stitch them together after each other to get some sort of matrix. Like you're stacking, after each other. And this is exactly how we're stacking these y's, y1, y2, y. So we're gonna get y1, y2, and so on. Okay, so which means this is going to be the concatenation all of those y's, and then we can project it into something else. Okay, it looks horrible, but I hope everything will make sense eventually. So this is the algorithm again. Oh, okay, this looks very bad. No. But like at the end of the day, you have to take this into account. But let's forget this. I mean, these are just the parameters and their dimensionality. And of course, if you need to program this, you need to know like, oh, how big, what is the dimensionality of my input, what's my dimensionality of the embeddings. And by having this, you will get the dimensionality of all your weights or your biases and blah, blah, blah. Everything will just make sense. Everything has to fit. Like if you're multiplying a matrix by matrix, your dimensions have to fit. So you have to make sure everything fits together. But again, so the multi-head attention is a function which takes the input and produces some other output. And for number of heads, so the h, which we had here, so number of heads, we run this in parallel. This is very nice. We run the attention of this input with some parameters and then stack them together. And then there is some projection to some output, to some other output, let's say dimensionality. So this is just the algorithm, written. This is the depiction written as a function, basically. So don't be scared of this. Maybe this is an overkill, but if you really want to, yes. Yes, exactly. You don't chunk in. No, every head sees the full input. So here, this is the full input text. If I'm coming back, what's coming? This is coming here. So this is the full input x, which means this is always the full input x. This is it. This is the full information coming into each head. Okay? Cool. Good. So now, what the heck is going on here in each attention head? That's the question. This, I think, is almost the last question we need to address, and then we have the architecture done. The last zooming in. So what is this attention head doing? So it has, I don't know why it's called head, but I know why it's called attention. So there will be some attention mechanisms in there. And I don't actually know why head. Why not? I think it maybe from the tape machines. Tape machines used to have heads, on the tape. And you can have like multiple heads on the tape, getting this, I don't know. Can somebody, ChatGPT, like why is it called a head in attention? Just out of curiosity. Maybe after lecture, okay, whatever. It's not important. But what's going on here is that, again, we have the input x. So again, the number of tokens, some hidden dimensionality. And we're going to do a couple of things with that. So there will be some projection. So this is some projection again. Projection. A linear projection to get Q, which is called query. Another linear projection to get key. Another linear projection to get value. There's a semantics of why is it called query, key, and value. We don't gonna touch that. We just call about the first how it works. And what is a linear projection? So this is a vector. How do you project it linearly? Oh, not a vector. Excuse me. This is a matrix. So what do you want to do to project it somewhere else? Means, yeah, multiplying by matrix. So there will be 3 matrix multiplications. So you take x, multiply by some matrix to get q, by some other matrix to get key, by some other matrix to get v. So there's 3 matrices to do just linear projection. Okay, good. And then after, so you take the key and, I mean, these will be different. So you will end up with different q and k matrices and v. And there's this production, scale product, softmax, and matmul. Okay, let's have a look into the detail, what it means. So this is the overall depiction of the algorithm, but let's have a look into the self-attention in detail. So on an example. So we have, again, this is I just want to make sure that we know each vector corresponds to each input in each token in the input. So the cat set and so on, the padding. So for each of them, we have some embeddings, and after projection to query matrix K, we have these Q1, Q2, Q3. So in the Q matrix, again, like each word corresponds to each row, right? Good. What we're gonna do is, and then the same thing is matrix K, but we transpose it. So we take, so K1 would be the first corresponding key to the first token, key 2 would be the key for the second token, and so on. And we transpose the key matrix and multiply them together. What does it mean? So you take the query of the first token and multiply by the key of the first token again to get this number. Again, you take the query of the first token, multiply by the key of the second token to get this number. So what these are, what is basically doing these, what is the product doing here? It's sort of, you're multiplying two vectors in a way and sum them up. I mean, you're multiplying entries and sum them up. What is this? Does it, it's another operation we spend a lot of time on that, like getting intuition. It's a sort of dot product. I mean, it's not sort of dot product, it is dot product. You take a vector, if you multiply two matrices like that, you're doing a dot product of this vector with dot product of this vector. And the dot product is telling you like, oh, you know, how the key and the query are sort of similar or dissimilar. Are they pointing in some similar direction or not? So we're basically saying like, for each token, we're saying how much sort of similar is it to any other token by multiplying these two matrices, right? I mean, here for Q, here we take the third word query and what is the dot product to like the second word? So we get 3 second. This is the dot product, and it's telling me, oh, the word set is somehow relevant to word cat, and we're doing this by this dot product. Okay, this is doesn't make sense, this intuition. Roughly, I mean, we can say like, oh, it's just, you know, we just multiply matrices and call it a day. But there's a reason why it makes sense, because you want to learn which word. That's why it's called attention. We wanna understand which word is somehow similar to any other word in the input sentence. What are sort of associations between words? And we're doing this by taking the embedding of each word, one in query, one in key, and multiplying these together, or taking the dot product of these embeddings for each token to see, oh, you know, is cat somehow important for set? Is the somehow important for cat, and so on? And this is how, you know, we're doing this by this dot product. Yes.
Are also trained parameters.
Yeah. Yes.
And they so there's no direct relationship.
So you want to learn. I mean, the goal is that you want to learn. That's a trick. You want to learn here the projection of key and Q, such that this will be useful. You want to make this useful. How do you make this useful? Well, at the end of the transformer architecture, there will be some loss or some task, and the task will tell you how useful is your matrices or representation. And if it's bad, you know, it should fix it by doing backpropagation and training. So after training, this should give you eventually some good projection matrices. So there should be some good projection matrix for Q, for K, and for V, such that it will, you know, it will make sense that the cat and the cat, you know, if you have a cat, it should pay attention to the, and the set should pay attention to maybe some other vector. So, you know, it should tell you like how these words are influencing each other. Yeah.
And then you're looking at so each token, how close they are together regarding one key in a column. So these S values.
How close they are to each other? I don't know. It's telling you like each. So basically, this is number of words, like L, and this is again number of words L, and you're saying, and this is symmetric at the first. It's telling you like, oh yeah, how is this sort of like raw association between each word with each other word? I don't know if I got your question. Sorry, can you?
We're looking at how close are the words together, but this is performed on a criterion named K, right? So.
I mean, yeah. So the question is like, I mean, the question is, what is this Q and K actually doing? What is in there? You know, what's in these vectors, and what's in these vectors? And I think it's complicated because, I mean, so the intuition is like it captures it captures strength of association. So if you look then, if you train the model and look at these attention weights, so-called, you will see that for some words, it fires some other words, like it gives like strong associations to others. And then, you know, people explore these architectures in detail saying, oh, actually it's very helpful for in machine translation or some syntactic task where some words with long dependencies to some other words have a strong association like syntactic associations or semantic associations. So this is how it actually turned out to work eventually. Yes, the Q and K produce you some good representation to get a good attention. Like that. Yeah, Paul.
I have a question. So this matrix would always be symmetric?
Well, now it's symmetric, but it's continuing. Okay, so first we get this, you know, Q and K dot products for each word. And for numerical stability reasons, we divide all this by some number, like square root of number of dimensions of the attention, whatever. So this is still symmetric. Now, what we're gonna do, so again, I mean, this is still corresponding to each row corresponds to each word here. And what we're gonna do is that these are some numbers, could be negative, positive, whatever. And we're gonna run it through softmax per row. What do you get after softmax? Yeah, and for the vector, what does it mean? Like if you put a vector through softmax? Yeah, you get a probability distribution, exactly. So now, I mean, if this is a real line, sorry, no, it's not really a line. Some are negative, some are positives, and whatever. And after this, you get a histogram, summing up to 1. And this is interesting now, because now you get actually really the sort of like, you know, which words are important for other words. Now, you would see that after turning these dot products, the raw associations, into the histogram, you would understand, oh, you know, this is a low value, so the attention value is very low, which means the third word is not important for the representation of the first word. But now, oh, this is higher, so this word is really important for the representation of the first word. So this is how you get like sort of a heat map for each word, a heat map for different words. How important are they for the words you're looking at? Okay? Cool. Good. What are you gonna do with that? Normalize associations. Yeah, there's the other metrics. Remember the value metrics. So we have the three matrix. So we got the scale dot product, softmax, and then there's another projection of the input to this value. And we're gonna take this normalized associations and project it to the value matrix. Oh, what does it mean? What does it mean? Okay. So the value matrix, again, in the value matrix, we have, so this is token 1, this is some representation of token 2. You know, like you project the token embeddings into some other representation, but it's a linear projection. So these correspond to token. And here we have how important is token 1 to 1, how important is token 2 to the U2, and everything is like this sums up to 1, right? Because this is like for each of those, this is the probability distribution. So what we are doing by this multiplication is very interesting. You take this vector and multiply by the first dimension of this value, which means all these things will be sort of weighted by this probability distribution. So if a word like this was higher, probability lower, 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 if a word has a low attention weight, it will end up with very low value after this projection. So this will be low value, this will be low value, right? I mean, we're multiplying some low value with some value here, but this will get a lot of attention, so this will be kept basically. I mean, you're sort of like normalizing, or no, not normalizing, but you're multiplying, well, making this value smaller basically. After softmax, there will be some peaks in the distribution, and most of the other values will be close to 0, which means this will be, you know, very small numbers now, except for those which have the high value. And we get the output of this attention head. So we're basically weighting, so this will be weighted by this value to get this. And again, we're weighting each vector by the string of association, obviously for each word. Yeah, I don't know if it intuitively makes sense, but this is how it works. I don't know better kind of way to explain the intuition behind, but it's basically weighting. So here we're getting raw, here we're getting raw associations, like which word is important for which word, just by dot product. We're softmaxing this, turning this into a probability distribution, which means words that are not important for other words will get almost zero value, because softmaxing is like e to something, like and normalizing. And words which are important for other words will have some value between 0 and 1. And we use this information to weight sort of these matrices to get some contextualized word embedding. So here, what we're getting is how important actually in the embedding space is some word for some other word, which is the self-attention. Okay, questions?
So I'm not quite sure. So this last output, what does it represent?
So, okay, so again, so each of them corresponds to each token. That's clear. And here we projected the inputs to this value matrix V. And what we are now doing is multiplying this by the self-attention values. I mean, this is not self-attention, by this probability distributions of associations, and it's weighting how important is each word to another word in context. So it's baking this into this vector. Maybe if we can do maybe like small hands-on like 3x3 matrix sort of like computation to see what it produced to get some intuition, which I don't have it here. Yeah.
So I think what is making it a bit harder to like think about it more is I think it's kind of mixing everything with everything.
Yeah. It's mixing everything with everything in a way, and it turned out. I mean, that's hard. The intuition is actually hard because you cannot force it to do what you think about. So what we're talking about, like what is it doing, is sort of, I think, by retrospect or some intuition of the researchers saying, oh, if you do this, maybe you will turn out this. So there is a pile of research kind of inspiring, this self-attention. There was like attention, for example, that didn't start in transformers. It started in 2015 in RNN for machine translation, for example. But we skipped that in RNNs because it didn't make sense. But there's some intuition why it's kind of, it was implemented here and turned out to be helpful. And the intuition, what is it doing is like by retrospecting some learned representation and looking, oh, actually it's really picking up, the dependencies between these two tokens in machine translation. Yes. Yeah, first. Go ahead, first. Yes.
And this shows somehow how important a word is regarding to another word.
Exactly.
And so are the colors important as well? So if I say I look in the first row,
okay.
fourth place, is it the importance regarding the fourth word? Or?
That's a great question. I mean, the question is like, what is in this embedding here? So this is basically a contextualized embedding of a word. And the question is like, what is each dimension in the embedding corresponding to? And the answer is, who knows? Nobody knows. Yes.
One word.
Exactly. It's just so what matters is how important is each other to another, but this dimensionality is something to be designed, like could be 20, could be 2000, could be whatever. And where it's coming from is from this projection matrix of key, Q, and value.
So it's about how important is this particular word in the whole embedding and not at a specific other word. So it's not distinguished between the importance between this word to a particular other word, but through the whole embedding.
I think it's like so it should learn, so the goal is for any sequence of tokens to learn a good contextualized word embeddings. And how is it working is that it tries to learn what is important for each word with respect to other word. And it's doing by this self-attention, by using the similarity, scaling, and summing together. This is as far as I can tell, like how it really works.
Okay, but in the end, we have just one word for one word.
At the end of the day, you have importance. I mean, here you're saying, here you say, okay, for first word, the importance is that. For second word, the importance is that, and so on. So you have sort of importance between all these words, like attention from each word to another word. What is the importance of these two words together? One being in position 1, another being in position something else. You have a question?
Maybe I'm misunderstanding something, but it appears to me, does the key and the query multiplications, do they depend on where the token is in the sequence?
That's a good question. Does it?
So let's say the words the and cat would now be in the second position, no longer in the first, but it's still detector dependent.
It's a good question. So you have, I'm trying to translate your answer to something I could really tell or not. So what you're, I mean, you have some. So this is a projection which takes a bunch of word embeddings and project to some query, and it works for anything which is here, like any sort of embeddings, any sort of words, anything. There is just one matrix projecting this. Well, one matrix per attention head. One matrix projecting to queries, one matrix projecting to keys, and one matrix projecting to value. So there's just a single sort of general single projection matrix for any input in there. Any sort of any sort of words which come after each other, the cat set or cat set question mark, anything. So this is just a single matrix. And we have a couple of these heads, like I don't know, 12 heads. So each of them will learn something else, but it's not like for every input there will be a different projection. That's not how it works. It's just projecting the input into some space where we can think about similarities between words. Yeah, it's very weird, I have to say. No, it's true. I mean, it's very weird. Okay. So this is nitty-gritty details, because like understanding how this really works, it's tricky, because we have like very many dimensions and very many training data to I mean, it's really tricky to understand the explain sort of like explainability of these transform models. It's quite hard. Yes.
I think the Q and key part makes sense. We're trying to learn how like the associativity between the words, but the final part where we multiply by the final operation with
this
value,
one. This one.
So how does y1 still only represent the first word, for example, embedding?
Why does it represent the embedding?
Because I think we're
okay, so let's have a look. So let's have a look what is V. Okay, so V. So because V has to have a, so we say V has the same dimensionality as, so let's say L times how many, like D. D is like, I don't know, 1024, like dimensional V embeddings. So L times D is V. This is also L times D. This is also L times D, and this is also L times D. So all these matrices are the same, which means each row corresponds to position in the input. Now what you're doing is that, is it true? Wait a second. Where are we? So we take this, yes, absolutely, because this is, so now this is L times L. Coming here. What's coming out of here is L times L. And if we multiply, what do we need to multiply? L times L times L times D, we get L times D again, which will be this output. So it will always be the same number of rows. Yeah.
But I mean, like, for example, if the first row in the output represents an embedding for the first token, why does it need to learn about the association between two other words that are not related to it?
Yeah, because you want to take everything into context. That's a point. Like every word, So basically, you want to have something like where every word knows everything about all other words in the sentence.
And not necessarily things that are related to just everything in general.
Just everything. Like you need to learn. You want to understand the full context, like left and right. For each word, you want to understand what's before and what's after, to learn the best representation of myself. It's sort of similar, like word to back. You have the target word in the middle and the word left to right, and you want to take everything into account to learn the best representation of the target word. So here we're saying, oh, we'll look at the associations, all the other words, which will give me some good information to learn the target word embedding. This is the best intuition I can give, I guess. Okay, cool. Wow. Other questions? So, okay, so here, I mean, now we need to turn this intuition into the algorithm, but so what we need to do is that if you want to add a single vector to each row in the matrix, I'm gonna call it add vector, and there's I mean, because if you look into the description of this formal algorithm, there is something like, you know, b equals to x plus this kind of transformation. Everything is like multiplying and adding matrices, but it basically means we're adding a row to each entry in the matrix. I don't know why it's important here. Maybe we can skip this for now. Maybe it will be useful later, but it's not super important to understand how it works. And also, like the softmax for matrices row-wise, of course, means that what we did here, we take each row, put it through softmax per row, and get softmax. There is no like mathematical operation saying softmax per row, so we define it just, it's actually correct. That's the point, like how you want to write it in the algorithm. Okay, so here is the input output. I mean, forget this. This is not important for now. But this is again the algorithm, sort of like not graphically, but as a pseudocode. So we take the Q, key, and V by taking the input, multiplying by some weights, and adding biases. Again, weights and biases. And here, this is basically just the self-attention. So we multiply key and query and key. So this is the like row times row dot product, divide by some number for stability, and then we apply the row over softmax. So this is how you sort of would write a sort of pseudocode for this graphical things. Here, I mean, why I'm putting this here is that all these dimensions actually are, you can dig deeper here and to look all these dimensions, all these ways and things like that. If you want to really try on paper, how these dimensions would work out, then this is correct. This is a reference, basically. You don't have to remember anything of that, like obviously, like all the dimensions, but just to have an understanding, except for that, each row corresponds to each input token. This is the important part. Okay, so, wow, man, this is, okay, so we check this, excellent. Multi of self-attention, okay, so it's coming out, we sum it up with the input again, and then we're gonna do layer normalization. So what is layer normalization? It's actually, it looks much horrible than it is. Like, oh, algorithm, no. So what is a layer also is just a bunch of numbers, it's a vector. So let's say we have vector like, I don't know, -2, 46, 21. And we want to turn, so if I look at this from, let's say a real line, excuse me, so -2, 46, and 21, maybe I want to normalize it so it is closer, so its mean of these values is 0, and it's just like standard deviation of 1. So basically like normalizing a vector, not normalizing a vector, but making sure all these numbers are centered around 0, and the variance or standard deviation is just 1. This is what we are trying to do and basically learn. So what we are going to take is we have a vector, which we called output of a layer. So it's a vector, and it's producing another, sorry, it should be output here. Output. Input is vector, output is a vector. And what we are doing here is a very fancy thing of finding the mean of all these values, like average. This is a very fancy of finding the variance. Like in statistics, this is the second row moment. Oh, excuse me, this is the second moment. So you take all the values, subtract the mean, and taking a square and expectation by sort of averaging, so you get the variance. And how you scale it is that you take each value, subtract the mean, and divide by the standard deviation. So standard deviation is the square root of the variance, right? It should ring a bell from some statistics, I believe. If not, this is it. Like there's nothing fancier. So we're basically scaling everything to fit into close to the mean, and the variance should be what is it? The parameter v. And also this is this very fancy term for element-wise product. So we can also add some offset for each element and some offset for the total vector, but usually these are like 0. So basically what you're doing is you're squeezing linearly all these values to have like smaller variance. It's better for numerical stability actually. Okay, very fancy term, layer normalization. Take the numbers, take the average, subtract the average from all the numbers, find the variance, divide all the numbers by the variance, and that's it. Call it a day. Nothing. I mean, and is it differentiable? I guess so. Yes, of course. What is the derivative of that? Oh, I don't know. So it's, you can. I think we would figure out. I mean, actually, it would be super easy. I mean, derivatives are easy. It should be very easy to implement. Excuse me. All right, so we have a layer norm, and we do it per row. So we do it per each row of x. We're normalizing. So if we have the x, again, is the cat set corresponding to some vector, and some vector, we normalize each of these vector independently. So each of these sort of embeddings will have 0 mean and standard deviation 1. Okay, good. So let me come back here. So we covered this in this transformer layer. Now let's have a look here. So we have some linear layer, something called GELU, and something called linear layer. So what if I delete this and tell this is ReLU? So what is this thing? Linear projection, nonlinearity, linear projection, yeah. Yeah, but what is this? So a matrix, I mean, the matrix is coming out of this, yes, sure. But as an architecture. So did you see sort of this architecture before? Yeah, but in the deep learning lingo, sort of, does it ring a bell? Like linear projection, nonlinearity, linear projection, nonlinearity, linear projection, nonlinearity. Yeah, it has a name. Okay. I think it's MLP or feed-forward network. I think this is MLP or feed-forward network. Sorry for my handwriting. Feed-forward network. Yeah, and here we don't have ReLU, we have GELU. So GELU is, actually GELU is very similar to ReLU. So what is GELU? Gaussian error linear units, which looks, wow, it's like something with CDF. Continue. Oh, see, what is CDF? Cumulative distribution function. Is it phi? No. What is this? I forgot. What is this? What is this? Theta? No. I think this is. I would call like this phi. This is the LaTeX term, but I don't know how to pronounce this. Anyway, so yeah. Phi. So phi, which is a CDF of standard, something very horrible integral. Say, I want to cry. So basically, what you do is to take you take x. So you approximate this usually. You take x times sigmoid, some fancy number times x, and what you're gonna end up is like, oh, it looks like ReLU. It's almost like ReLU, but ReLU would be like this. ReLU would have this sharp knee, and this has like a soft knee. This is it. This is the only thing which makes GELU differently from ReLU. And some people start using GELU in there, and it gives like better results than ReLU for some very weird unknown reasons to me, like magic in deep learning, But So GALU is a thing. Yes, GALU is a thing. You can make it very precise. You can make it approximate. It's sort of like ReLU with a soft me. It's differentiable. ReLU is also differentiable except for one single point, which is 0, which you very unlikely hit. And if you hit it, like, you make a decision. So yeah, exactly. So, but yeah, exactly. If you're, I think like the advantage is like, if your values are closer to 0 negative, like if you are in this region, you don't get like 0 derivative right away. You have some sort of first positive derivative, then a little bit negative derivative, and then you have 0. So maybe for these values, you know, it's kind of like softening the hard kind of ReLU thing. Oh, okay, so let's come back. So we have GALU here, we have multi-layer perceptron, we're summing up, and we have another layer normalization. Yoo-hoo! Okay, so we have all the building blocks now. Some makes more sense than others. So we can put it into this very fancy algorithm. So, where we are. Okay, so this is so far so good. So this is the input, like the token embeddings and position embeddings. We sum them together and get embeddings for input embeddings for each token. And we stack them together to get this X. Number of tokens times some dimension. Then we repeat for L transformer layers. We repeat the multi-head attention. So this is the multi-head attention is like the biggest kind of, you know, working with all these associations and attention and all these key query and value things. We push it through layer normalization, then we push it through MLP or feed forward, and we add layer normalization again, and end up here out with some much better learned representation. And we repeat this. So this is it. This is one layer, and we repeat this L times to get some even better contextualized token representation. Okay, questions so far? Except for like, oh, this looks complicated. Yeah, it is in a way, but maybe not. I mean, it depends. Okay, so this is the architecture, and now the question is like, oh, you know, what are these final layers doing? And let's have a look. So you might want to just take, what you might want to do is just to take the word embeddings or the contextualized word embeddings and use it for your representation of your sentence. That's fine. You know, you have basically, for each word, you have this contextualized word embedding, and you can do stuff with that, whatever that is. Or maybe you want to project it into vocabulary again. Why would you do this? Like, oh, maybe you want to use this for generating sort of the next word, maybe. So how would you do that? Well, if you have the cat set, and then you would say question mark. No, sorry. No, like that. The cat and the question mark, and you have embeddings of those. Maybe you want to turn this into probability distribution over vocabulary, which could be used for predicting some words. So maybe the next word, maybe some missing words and things like that. So it will be clear when we talk about pre-training. So this is one way. It's called unembedding. So we're gonna turn this linear. We're gonna project it into some interlinear layer of size of the size of the vocabulary, and using softmax per row, which will give us basically for each row a probability distribution over vocabulary. So probability distribution over vocabulary. Okay, wow. I think we have this. This is it. This is the entire transformer function. Like with ignoring, I mean, at the end of the day, if you prefer this or the visual depiction, that's a matter of taste. This is what you see if you look up in the code. I mean, there's for example, a famous blog called, I forgot his name. Transformer, explain transformer or something like that, where you basically implement the transformer in a notebook along with the original paper, and this is what you would see basically as a building blocks. I mean, you could translate this into PyTorch as well if you really try hard to build transformer really from scratch, using these kind of using these operations. They should be all available. Okay, so I don't want you to remember any of those, like because it's conceptually, it's like how you implement it, but conceptually, you should know like how this architecture works. That's important. What we skipped here is all these hyperparameters. Oh yeah, this is parameters and hyperparameters. So hyperparameters are the maximum length. We talked about this. So you have to design like how many tokens will be the maximum of my thing, and how many layers, how many heads in each layer, and dimensionality of the embeddings, dimensionality of the multilayer perceptron, and what is DF? I don't know, something. I don't know, some other parameters. Oh, it should be BF, I guess. Yeah, whatever. All these matrices. So a lot of parameters that needs to be trained. Okay, I think we have to make a choice whether we cram in everything into the last 5 minutes or we leave it for next time. Shall we cram it into 5 minutes? Like I have 19 slides in 5 minutes, or we should keep it for next time. Next time? Sounds great. Okay, so let's keep it for next time. And any other questions? Now in the 6 minutes, we can talk about it in 6 minutes. Yes. Yes, because I mean the answer. So yeah, the answer comes here in the pre-training. Like, what is it good for actually? I mean, we know it should be good for learning representations and be useful for many downstream tasks. But we talk just about the architecture. But the point is, if we start talking about, I mean, let me show you this. Like, if we start talking about like pre-training, if with self-supervised multitask pre-training, then this would still be somehow like, oh yeah, I have no clue what's going on in here, but I know how to use this. We took a different route. We said, okay, we know how this works to the very last detail of the thing, but we can now abstract from this and say like, oh, it's just learning representation of embeddings, and talk about how it's pre-trained, how it's employed, how it's fine-tuned, and things like that. But if you're talking about fine-tuning and things like that, and this is a black box for you, it's gonna, I mean, maybe it's harder to conceptualize like, oh, it's a magic. No, it's not magic. Like all these things together from every token to every token are telling us that there is this self-attention saying like each token is taken into account for every other token in all these layers. And now in this simplification, we understand why exactly. So we will talk about this later, and then they will make sure like, how is it going to be actual helpful and why is it so big deal, this transform architecture? Okay. Yeah.
Okay, we ended up with the probability distribution for every word.
Yes.
And next week we will look what we can use.
Exactly. Yeah, as I said, like there's two things you want to have from the encoder, from the transformer. So either you just learned the representation of words and forget this. Okay. This is most of the time what you're gonna do, because you want to use these embeddings for any downstream task. This is most of the time. But also, and this is important for pre-training these models, you can also project this into vocabulary and then use this projection to vocabulary to do some sort of like language modeling thing, which will be very important for the pre-training. So as I said, like 99% of the time you're interested in having the embeddings out of this, but for pre-training, there is this final layer projecting into vocabulary to train something. This will be important for that, okay? Cool. All right, any other questions? So the case, so thanks a lot. I'll see you at the exercise in the afternoon.